Hi. In this session, we're going to go even deeper in terms of using set notation, but to get there, there's a couple more formulas that we need to use, learn about, and I thought the best way to do it, well, you know my style, is through trying to solve a problem. So off you go. If there's a problem on the screen, date, title, set notation, and Venn diagrams, calculating with set notation too. Uh, Off you go on this problem. Try to solve it. Use the power of the pause, and I will start doing it in a moment. So, see you on the other side of your solving success. Brilliant. And I say see you on the other side. All I did was wait 2 seconds because you were supposed to do the power of the pause. You were supposed to pause. Video, that's technology. Let's get going. The question gives us some information about me playing a game. It estimates the probability of me winning the first time and the second time. Now, interestingly enough, this is the kind of problem I'll just mention that you would typically look at modeling using a tree diagram. You know, first time, second time, and you would have your branches. So the probability of win, lose, and then you'll go win, lose, win, lose, etc., etc. I thought it was important to just mention that. And you'll have your 0.5, and then chance of winning the second time 0.5, and so on and so on. And we will come back to that idea of the tree diagram in a moment, because that will help bring home the idea. One of the ideas, the big new idea we're going to come out of this one, and it has to do with part D, with independent events. Do you have a solution for that? We'll talk about that in a moment. Let's get our Venn diagram, shall we? I need a Venn diagram up, so I'll switch to this screen. And we know that the probability of winning, what we'll have to do, we got to label up the Venn diagram. So I'll have my sample space, and I would label it using F and S, where F win the first time, so the event that you would win the first time, and then S would be win second time, and that's my doctor handwriting there. So F, the event, and I should say the event, but I'm conscious of space, but no, you should be writing F. Let F be the event. We want to make that statement, the event that you win for the first time, and S is the event that you win for the second time. Once we have that, then we can start building the probabilities, because from the information provided, what do we have? We have a situation where probability of F, and I'll just write in the probabilities, probability of F is 0.5. We also know that the probability of winning a second time, so probability of S is 0.5. Ooh la 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 la. And then what other information do we have? We're told that the probability of winning both. And what does winning both mean? That's the overlap. That's the intersection. That's the probability of F intersection S. And we're told that's 0.2. You should recall, you work with Venn diagrams before we got into set notation, is that if you have all the information about the different regions in the Venn diagram, then you work inside out to complete the diagram. So inside out means I start with the overlap. So probability of F intersection X is 0.2. That's the overlap. And then I can deal with probability of S, because if the whole circle has to be 0.05, then the missing part of S will be 0.3. Now I have the two probabilities, two proportions. When I add them, I'll get 0.5 for the entire egg, representing the probability S, winning the second time. And similarly, for F, I'll also have to use 0.3 because the probability of F, it's the same as the probability of S. And we can see we have achieved our goal here of having the chance of winning the first time as 0.5, the chance of winning the second time of 0.5, the chance of winning the first and the second time as 0.2. And then the final bit to finish a Venn diagram is remembering that all the probabilities have to add up to 1. Okay, and if all the probabilities have to add up to 1, what do I have at the moment? I have the probability of F union S. I'm using that set notation. So the two eggs combined as 0.3 and 0.3, 0.6, 0.7, 0.8. So F union S prime, the complement of F union S, has to be 0.2. I haven't used the set notation, but I'm talking through it, and hopefully you're happy at what I'm doing. Now, find the probability that he does not win either game. Does not win either game. Let's look at what this means. It's the probability that he doesn't win the first time and he doesn't win the second time. That is the same thing as, and can I just clarify, none of this is absolutely necessary for this specific question. The answer is going to be 0.2. Okay. I am doing this just to continue that process of embedding set notation, the concepts and how we can use set notation, because the more we talk in that language, the more on that big day in an exam where you need to use the concept, you will be able to do it. And going further than that, the more on that big day in a job interview and so on and so forth, you know, those other big days, the bigger days than the exams, you can successfully interpret and describe your ideas using set notation if required. Probability of F, not F, and not S, that's what does not win either game, which is the probability of F union S prime. Remember that switch the intersection to the union, and then we can take the prime we can take the prime notation outside of the bracket. And there's it's one of the sessions I'll do at some point. I will introduce you to I gotta give the credit, so Venn and De Morgan, the guys, the mathematicians that came up with these or first shared these relationships. You know, that will be useful information for you going beyond what's fully expected in the A-level curriculum, but very powerful for interviews, etc. potentially. Okay, so I'll share that with you. And the answer to this, we know F union S is 0.8, so F union S prime would be 0.2 is the answer for A, 0.2. With part B, we want to find the probability that he wins exactly one game. He wins exactly one game, exactly one. Now, what does that mean? Well, first, let's get the answer, and then I'll give you that new task, that new challenge of writing this question, find the probability that he wins exactly once, writing it using set notation, because it's an interesting one. In terms of what you want is to identify the regions you're interested in. Exactly once would be that he wins for the first time only, or he wins for the second time only. He wins for the first time only or the second time only. That's the way I'm thinking about it. And I've identified the regions. I think we'll agree to regions. He wins only the first time. He wins only the second time. The answer to the question is going to be 0.6. Now let's note, once you have the Venn diagram, there's no need to write the set notation to answer the question. But we're in a session here where we're practicing and developing our use of set notation. So the challenge I give you now is, can you write using set notation? You could write a set notation expression that represents the region that I have just highlighted. Yeah, I just did that. Let me see you do that. Okay. Now, you have your power of the pause. You pause and you do it. You've had your moment. Okay, good. I'm going to do my moment and show you how I went through it. It might be different. I don't know. We might come up with something different. But remember, in set notation, you've seen it in part A. There's more than one way to represent regions in a Venn diagram. So let's go. I'm thinking that I'm going to think, how do I get the first region? How do I get the first region? And I'm thinking, well, it has something to do with F, but I'm cutting out, what is this region that I've shaded? Well, and you might remember doing this one. That first region, and I should have done it in different colors. So what I will do, I'll go back. Let me just get, put in a different color, and I'll call this, what do you call this? Lilac pink. We'll just call it fluorescent pink. Don't get into a debate with me with colors, please. Come on, just work with me. You know what I'm talking about, yeah? So 0.6 is the answer to the question. The answer to my new question, right, represent the shaded regions in using a set notation. It goes like this. This first region in fluorescent pink, yes it is, fluorescent pink. So we're going to use the probability, I use probability notation, the probability set notation form. And it's going to be the probability, look at carefully what I'm saying here. It's not an S, but it has to be an F. Not an S, because we're cutting out everything we want, and it cannot be in the S egg, but it has to be in the F egg. So not an S intersection F, or I can put that into F intersection S prime. That's that region. And it is one, we have touched on that region previously. So if you look back in the previous video, I think it would come up. And then, well, that's not the only region we want. That's one option. So not an S, but an F, or now I can get the green bit. I need to do a union symbol, or the probability of it being in. And what is this green section? Well, this is telling me if it's over here, it's not in F, but in S. It's the bit, the piece of the Venn diagram that is not in F, but is in S. So F prime intersection S. That is, it is two probabilities. It's the and that's how we use the union to combine these regions. So because it's it's either in the first region or the second region. So I've used the or with union. So not an S, but an F. Not an F, and in I'm saying but in S, but and I'm just weighing them up, and yeah, I think I'm happy with that. Are you happy with that? And I'm gonna make one edit to it just to show you how slightly more complex it could be. Actually, I could take out the P. Yeah, don't need it. We could actually make it one. What's the probability of S prime intersection F union F? I'll put it in a different color though, so you can see we can do it as soup separate. We want to do it actually. I only need one probability. It's one probability. So F prime intersection S. Yeah. Fine. It's one string, one complete string. The probability of those two events, the first event or the second event, is what it's saying. The fluorescent pink or green. Okay, so that's how we'll represent it in set notation. For part D, and I put it as part D because in the original exam question, there was a part C, which we're going to address next. That's the other big idea, but let's deal with part D. And part D, this big idea of independent events. So we want to, by calculation, determine whether or not the winning games are independent. How do you do that? Well, to do that, I'll copy and I'll paste, and I will delete that information. We don't need that anymore, but we do need the data on the right hand side, because that's what it's about. Okay, and let's make some space. Always space is a premium on the computer screen. So independent, we want that, the probability that the events are independent events. And for independent events, this is a test that you need to make. This is the test you need to make. You want to test if the events are independent. The probability of A multiplied by the probability of B is equal to the probability of A intersection B. That's the test for independence. If events are independent, in other words, what happens the first time doesn't affect what happens the second time. In this context, winning the game the first time doesn't affect what's going to happen the second time. Then we'll have the probability of A times the probability of B is equal to the probability of A intersection B. So you can see now, whereas the first two parts of the questions you didn't have to use set notation, the second part of the question required an understanding of probability, and I say loosely with set notation because you can, in fairness, intersection is the word and. So probability of A times probability of B is equal to the probability of A and B. We could have taken it that way without set notation, but intersection, we're at the stage where we can appreciate the set notation. That's the test we have to do for independence. In this particular case, we have probability of A is 0.5. So probability in our particular context, I have to switch the notation. So this is a general form that you want using throughout, and we use different letters. So to answer the question, what will we do? We'll go in our context. Can you still see that? Yeah, maybe. Okay, we will go that probability of F times probability of S equals 0.5 times 0.5, which is 0.25. That's what it is. And then that is not equal to probability of F intersection S, which is equal to 0.2. It's not equal. We worked that out. Probability of F intersection S was 0.2. Probability of F times S is 0.25. They're not equal. That means, what game was Dwayne playing? I don't know, but not independent events. Okay, they're not independent events in this context. If they were, the probability of A times the probability of B would be equal to the probability of A intersection B. That is now the new addition to our work with set notation, the test for independent events. Make sure you know it and make a note of that formula. You're going to have to use it. Now I want to go back to our idea of mutually exclusive events. And I want to do this because a common issue that comes up is muddling up these ideas of mutually exclusive, events being mutually exclusive and events being independent. So let's just think about these two ideas for a moment. Mutually exclusive means that the events cannot occur at the same time. So for example, if I think about flipping a coin, getting a head and getting a tail, it's either or. When you get a head, you cannot get a tail. Okay? And well, let's just look at this. If I'll just switch this from A to B. I mean, I have the picture there, but if I have, actually no, I won't switch it because I want to stick with, let's just say A is getting a head, event getting a head, and B is the event getting a tail. Then the probability, we know the probability of, when you flip a coin, the probability of getting a head is 0.5. The probability of getting a tail is 0.5. Okay. Now, the probability of getting a head and a tail, well, that cannot happen. When you flip the coin, it's either or, not both. In one flip, we're dealing with one flip, and that's the difference you'll see on the right-hand side. I've talked about independent events being not mutually exclusive and the coin being flipped twice. In a situation where the coin is flipped once, that's what I'm talking about here, it's either or. You're either going to get head or you're going to get a tail. Now, if I do the test for independence, probability of A multiplied by the probability of B is going to give me 0.5 by 0.5, which is 0.25. But the events are mutually exclusive. So by definition, and the Venn diagram makes it clear that the probability A intersection B is equal to 0. So we have a situation where the probability of A times the probability of B is not equal to the probability of A intersection B. So mutually exclusive events, and they are not independent. Now, and then you have to ask yourself, well, in what situation is it at all possible? Can there be a situation where mutually exclusive events are independent? And, well, the only way you can multiply and get 0 is if one of the probabilities are 0. So now you have to go back to, well, what does a probability of 0 mean? It means that an event is impossible. An event is impossible. So if one event is impossible, at least one of the events are impossible, then we can have a situation where the events are mutually exclusive and independent, because we're going to get the idea that probability A intersection B is the probability of A multiplied by the probability of B. But in general, mutually exclusive events, in the vast majority of cases, they are not independent. One event is happening as a result of the other event not happening. And note what I said there, as a result of. One event, that means there's a dependency. The only way I flip the coin, the only way I can get a head is if I do not get the tail. That's what this diagram is trying to the idea I'm trying to get across. So and think about that and work with that. It's possible that you will see in exam contexts and questions where the phrase, you might get a phrase indicating that the events are mutually exclusive and independent, and they want you to draw a Venn diagram. The reality is the Venn diagram on its own is not sufficient to get across the idea of mutual of independence. And I suppose my advice in that case would be, the key thing you want to take from that, the indication that the events are mutually exclusive and independent, is that there is no overlap. A intersection B is equal to 0, which that's the key thing there, and I'll leave there. It's an interesting one, because this is a matter that is discussed right through university, etc., and many people working on probability. It's a gray area, and it's not a gray area. It's an area that actually goes into mathematical proof and contradictions, etc. So in many ways, it's not in the domain of the A-level syllabus. The critical bits you want to take from what I'm putting forward here is that mutually exclusive events, the intersection is 0, and that formula, the union, is the probability of set A plus the probability of set B. That's the key fact you want to take. And then the formula for the test of independence. And I want to just do one. Let's just look at another idea with this test of independence. And look what I've put here on the right, that independent events are not mutually exclusive. And the context, look at the context now, coin flipped twice. Now we're talking about one flip and either or. We're talking about two flips, and what's the probability of getting a head and a head? And so something that you can represent with a tree diagram, and I'll use that to justify the logic, because from the theoretical probability, and I'll put H1 and H2, so I should have a 1 and a 2 there, and the probability of getting what's the probability of getting, let's deal with the both. The probability of getting a head and a head, and you recall from your tree diagram, probability of getting a head and then getting another head is a half times a half. It's a quarter. 0.25 is the probability of getting a head and a head. The probability of getting a head the first time was a half. So the whole circle for heads the first time would be 0.25 and 0.25. That's going to give me the 0.5 in the egg representing head the first time. Head the second time, again, I need to use a 0.25 and a 0.25. You can see it's 0.5. We're getting 0.5 in the head the second time. And look at what happens when we do that test. For are these events mutually exclusive? No, because you can get ahead and ahead first time and second time. And then in terms of being mutually exclusive, in terms of being independent, let's do the test. Probability of A multiplied by the probability of B in this case is 0.5 times 0.5. No, 0.25 plus 0.25. The probability of getting ahead is a half. A half times a half is 0.25. The probability of A intersection B is also 0.25. It fulfills the requirement of being independent, and then that makes sense. If you flip a coin, we know flipping a coin, what happens the first time has no effect on what's going to happen the second time. Absolutely no effect. Every time you flip a coin, it's like it's the first time ever. You got a 0.5 chance of getting a head, 0.5 chance of getting a tail. Just to clarify, if it is a fair coin, a fair coin. Okay, so this example, you can see it meets the test of independence. We'll say independent because probability of A multiplied by the probability of B is equal to the probability of A intersection B. Okay, so that is fulfilled in terms of flipping a coin twice and getting a head and then getting a head. So those are independent events. If I did a head and a tail, it would be the same thing. It would be independent events. And I hope I've gotten across these ideas and separated these two concepts in an effective way. And I know that statement, mutually exclusive but not independent, on except for the special case where you have an empty set, an impossible situation. That's not something that comes up really in our domain of A-level mathematics, but something I thought that was important to bring up. The very last thing before I move on to another question for you to do, a very last idea I want to mention, something maybe of interest. We mentioned here about independent events, and I used the example of a coin, flipping a coin, and I said a fair coin. What might be of interest to you, and I'll encourage you to Google and check it out, is some research that was done on the euro, and if I recall correctly, the euro from Belgium. The Belgian coin, I think some scientists were looking at that back in 2002, and they were suggesting that it was not a fair coin. So that might be something you want to explore to extend your understanding of probability, how they went about doing that experiment, and are they right? Is that particular coin not fair? Is it a biased coin, the Belgian euro from 2002? So you can Google that and do some research on that. That's a point there. Let's get to another question. So here you go. Let's see how you get on with this one. You have the power of the pause. You use the power of the pause. You're done. Okay, right. My turn. Let's get going with this. We had A intersection B complement. Let me just label. So we have A, we have B. I'm going to do this a bit faster than before. And A intersection B complement. So everything that is not in A, not in B, everything that's not in B, but it is in A. That's this section of the Venn diagram. We looked at this in a previous question. Hopefully you were able to make that connection. Then A prime intersection B elements, the chance of getting an outcome that is not in A but it is in B. It's over here, 0.23. It's over here. Not in A but in B. That's what it means. And then A union B is 0.8. So what does that mean for me? A bit of a calculation here. And I'm just going to write it in set notation. This is absolutely not necessary in terms of doing the question but I just want to bring home the use of set notation. You know, that's something I'm trying my best to do. I can write that the probability of A union B is equal to the probability of A intersection B complement plus A prime intersection B plus the probability of, what's the third probability? What's the probability missing? What goes in the middle here? It's A intersection B. So that's a relationship that that could prove useful in future questions. I've just written the whole thing down in probability notation. All it simply means is to find out that missing value in the sets. What do I need to do? I need to do 0.8 take away 0.24, take away 0.23. We're going to be adding the two of them, so 47, 0.47. So what's left is 0.33. 0.33 is the missing probability. And then finally, we recall that all the probabilities, there's a fourth region that's missing a value. All four regions, when I add them up, I have to get 1. The missing region is the region that represents the event that I do not get probability, that I do not get A union B, A or B. That's the event that's missing. Do not get or not A union B. What we're looking for is probability A union B prime, and that is going to be, if A union B is 0.8, A union B prime has to be 0.2. The value outside is 0.2. So that is the Venn diagram to represent the sample space, and we put S for sample space on the outside. Now we're asked to write down the values of the probability of A, and you realize after you got the Venn diagram, it's almost game over. Probability of A, 0.24 plus 0.33, which is 0.57, 0.57. The probability of B, that is equal to 0.56, 0.56. And finally, for part C, we're asked to determine whether or not the probabilities are independent, whether or not A and B are independent events. And to make that decision, we need to do the test for independence. So I'll just put a little rectangle in here, some space to do that. We write our formula. We're doing, the check is probability of A multiplied by the probability of B. We want to see if it's equal to probability of A intersection B. We know A intersection B is 0.33, so the calculation we need to do is probability of A multiplied by probability of B, 0.57 times 0.56, and when we work that out, which I will do with my super duper one-note calculator. Let me just get in a space here. I'll just show you this. I'll type in 0.57 star 0.56, press the equal sign and enter, and voila, there you go. I didn't want it, just needed to make a bit more space. So it is 0.3192. That's cool, isn't it? One note, you can just type in it, it does calculations. Yeah, 0.3192, which is not equal to 0.33. It's close, but it's not equal to 0.33. So I can say that the two events, we were asked to determine whether they are independent, and we will say that they are not independent. Okay, the two events are not independent because the probability of A multiplied by the probability of B is not equal to the probability of A intersection B. Back in the day, you would have had 7 marks for this in the old A-level specification. In the new A-level specification, the values might be slightly different in terms of the weighting given to particular skills. I mentioned that, and I didn't actually, I have it, let me just go back. This part C was actually part D in the question, the actual exam question that this is based on. So that means that part C is missing. What was part C about? Conditional probability. how do we use set notation to solve problems given with conditional probability? That's where we're going to go to. That is that's a big one for this lesson. But before we get there, I think we need to think about this idea of conditional probability without set notation for a moment, and that will enable us to build the equation. So let's go back to working with Venn diagrams without set notation, and let's answer a question. Here is the beauty I'd like you to work on, and this is a question that we was addressed in AS statistics, so statistics in the first year of an A-level course. This would have been touched on, so you should be able to work on it. I've had to edit how it's formatted to get all the text on the screen. What I would recommend is you probably might want to list the different facts that they were given, so put it on separate lines. 39 had effect A, 49 type B, etc., etc., down to 7 had all 3 types of defects. You might want to list it. That might make it easier to interpret the information and solve the problem. Pause, have a go, take your time. Okay, we're there. You're done. You've checked over your work. Diagram drawn nicely. If it is you're not there, this is your starting point. So I'm giving you opportunity to continue. You still have that chance to actually try the question. You learn best from doing. Remember that you learn best from doing. And the strategy, the hint, the way this is going to be done, I'm not going to do the whole thing from scratch, but the strategy that you want is to work inside out. Inside out is the way you need to work on this. So let's get those figures in. So we start inside out. That means A intersection B intersection C, the middle. And when I say inside out, and the way it's structured, it's actually working backwards. So 9 in all 3 types. So we have the 9. And then it's 17 in B and C, B and C. So this entire overlap has to be 17. So 8 is missing. 9 and 8 is 17. 11 in A and C. So 2 is missing because 2 and 9 will give me 11. And then the 17 in A and B. So A and B, this overlap here should be 17 as well. So another 8 is required. And after we've done that, we can finish the missing 3. We needed 40 in total for C, so 21 is the missing number. We needed 48 in total for B. We have 8 and 8, 16, and 9, 25, so 23 is what's missing. And then finally for A, when you work through, you should see 16 is what's required to get that total of 35. The entire diagram, we've filled all the regions except not in A or B or C. So A union B union C prime is missing. To get that, we add all the values that we have and we take away from 1060, and that will give you 973. That completes the diagrams there at 973. Now, in terms of answering the questions, they're all probability questions. So for B and C, let's deal with B and C. So the denominator is going to be 1060 because that's the total of the entire sample space, 1060. I should have had the S there. My apologies for that. That's my entire sample space, S. And no defects, that means not in A, B, or C, which means the 973. So the probability of no defects, 973 over 1060. And then no more than one of these defects, no more than one. Well, no more than one, you're thinking about the probability. I'll just write, where can I write it? 1 or 0. That's what you're thinking about. You're thinking about getting the probability. I'm looking for space to write this. The probability of getting 0 or 1 defects. That's how I can write it in just in text. The probability of getting 0 or 1 defects. That's what C is. That will be interesting to write in terms of set notation. What would it look like in terms of set notation? Ooh la la. And what is that? Well, it is, I'll just highlight none, 973, plus, so no defects, plus the 16, that's only defects in type A, defects in type C, or defects in type B only. A only, B only, C only. So 16, 23, and 21. The calculation you need to do for this is 973 plus 16 plus 23 plus 21 all over 1060, and that will give you 1000. When you work it out, you should get 1033 on 1060. So that will be your solution there. Now for the special one, the one that we're going to use to connect to set notation for conditional probability. What is the condition that has to be met for us to consider an element from the set? And we can see that a part in this story, we're seeing that a part selected at random from the sample has only one defect, and find the probability that this part that only has one defect was a type B defect. So the condition we're looking at is the part must have one defect. We're no longer interested in parts with no defects or 2 defects or 3 defects. We're only interested in the set of parts that has one defect. Okay? And for simplicity, and to make that my link to conditional probability, I would say let O be the event one defect, part with one defect. Okay, I'm just shorthand, and I'm calling it O1, short for 1. And the reason I'm calling it O is because if we were to write using set notation, the set that represents parts with one defect, it's gonna be a long string. So I want to keep things simple here, and it will help me to make that link to the general formula for conditional probability. So what are we talking about? What regions in this Venn diagram would represent O? Well, it's going to be this region here, the 16, A only, that's one defect, or B only, another defect, or C only. Those 3 regions are the regions that represent parts with one defect. So those regions together would represent O. If I try to write that in set notation with A, B, and C, I'm sure you would agree it's going to end up a long string. So I don't want to do that. And then, so now we're saying that the way we want to think about this, that will allow me to generate the general formula for conditional probability, is find the probability that it was of type B. So probability that the event is, we pick a part of type B given that it is of type O, and type O in this case is of that it has one defect. So the condition, the limiting factor, it has to be from O. Now, in probability, we don't use the word given. We say that for the condition. What's the condition? I want to get B, type B defect, given that it has one defect. That's how we describe conditions. And instead of using the word given, the symbol we use, but this is how we would write it. P, I want the probability of B given, so you'll see that line going straight down, given O. That's the notation for conditional probability. And now let's look, and just to be clear, it has to be a straight line. Whee! This is B, red, B given O. And the way we represent that, let's look at the numbers. We'll look at numbers, and then we will look at, well, if those are the numbers we're using for our numerator and denominator, then what's the probability going to be? Okay? And the denominator, if I want the probability, it has to be an O. So that limits my denominator. My denominator is no longer 1,060. I don't have 1,060 parts to choose from. I can only choose from the parts that I've highlighted in green, because those are the parts that have one defect. Okay, and we want to know, out of those parts that have one defect, that total, how many are in B? So how many parts have one defect? Well, it's the 16 plus the 23 plus the 16 plus 23 plus the 21. And let me just move that to the right hand side here, a bit further out. And then let me say, well, that count that we just did, that's 16 plus 23 plus 21, counting the total number of elements in O. What's that in set notation? Well, what we just worked out is NO, the number of elements in O. And then what about the numerator? What are we going to count? Note the terminology is in B given O. We want the set of elements that are in B that are also in O. So the numerator, which is, it's going to be one of these numbers. One of these numbers we have to count, 16, 23, or the 21. How many? Because no, just to be clear about this, remember that this section, I'll put it in blue, these parts of the set B, the 9, the 8, and the 9, we're not counting those. They don't fit in at all because they are not representing elements. They're not representing parts that have one defect. So they don't count. They don't count at all. So I cannot write, I'm not going to write the total of B. I want out of these, in other words, our filter is only one defect. So it's either going to be 16, 23, or 21 as the denominator, but we want only one defect, but in B, and in B. Only one defect, and in B. I use the word and. 23 is the number we're looking for. That's the number of elements that have one defect, and they're in B. And if I ask you, well, that count that we just did, what region were we counting? Well, I've said it. We've just worked out the number of elements in B and O. Number of elements in B intersection O. Number of elements in B intersection O. And that is your the general formula to work out probability, a conditional probability. Your denominator is your reduced set. So if you want to say the subset that you're interested in. So I'm calling it O in this case because it's a lot easier than the long string we'll have to use for set notation for A only plus B only. And it's not even A only. It gets more complicated than that because it's this 23. That's the complement. If I just want to represent this, let me just give you a sense of how complex it would be. That region with 23 will be the region represented by A union C complement, so not an A union C, but intersection B. That's what it's going to look like for the 23. And then I have to do two more of those to represent 16 and to represent the 21. So that's what 9 letters and unions and intersection symbols. You can see that's going to take up a lot of space. So, but I just threw that out there. That's what we're talking about. And hopefully this makes sense. I'm only interested in, and we looked at this without set notation previously, so yeah, jog your memory, yeah. Only interested in the elements that do not, that only have one defect, so the number of elements in O, so highlighted in green, because I created this new set, new event, really. And then we're interested in the numerator being the ones that, well, in O, what's in B. So A, B intersection O. And the final answer in this case will be 23 on 60 when you add up those values. 23 on 60 is the answer you're going to get. 23 on 60 is the answer to this question, and you perhaps, hopefully, you have that answer without any set notation. Because I've done two things in one. I've done it as revision for what what you should have understood and mastered previously, and also to start to build this idea of conditional probability and the notation for it. So, what do we have? And let's finish this off for conditional probability. Let's finish it off. Formula. We have the answer for the question, so you can mark your work on that. And the formula that we've generated here, and then we'll use it in another question. We'll apply it. I'll make a blank. Let me just copy this. Actually, no, I'll just looking for space here. Space is always a premium, but let's just make some space here. What are we saying? That for conditional probability, the probability and the general form of it, A given B, this is the formula, the probability of A given B is equal to, there's two versions we can do, but we're going to stick in probability notation now, is equal to the probability of A intersection B divided by the probability of B. Or the number of elements in A intersection B, which is the model we just worked with, divided by the number of elements in B. So because the number of elements in B becomes the limiting factor. That's the only set options you can choose from, so it's your new denominator. And you want from those options, where do I have the match, where do I have the overlap with the other option? That's the intersection. Okay, that is the concept of conditional probability. These are the formulae you can use to do calculations with conditional probability. Hope that, and I always, you can pause, remember this video, you can go over it, hopefully it makes sense. And now let's look at a question, let's look at questions where we can actually use this fact, okay? And actually, before I do that, let's just put on everything else. I'm going to give you a slide with all the big ideas, because we've run through all the big ideas now. Mutually exclusive events, independent events, and conditional probability. Okay, your probability formula is that you can use in questions. But let's just put them on one slide, summarize that, and then let's look at a question in context. Again, one for you to try as well and me to help out with. So this, as we draw to a close on our work on set notation, is the your one-pager. The general addition law for probability. Probability of A union B is the probability of A plus the probability of B. Take away the probability of A intersection B. For mutually exclusive events, A intersection B is 0. So when you're finding the union, you just need to add probability of A and probability of B. And the mutually exclusive events, it's represented by eggs, the sets, being disjoint. In other words, they do not overlap. They're separate eggs or separate circles. Independent events, the test probability of A multiplied by the probability of B. Is it equal to the probability of A intersection B? If it is, the events are independent. If it is not equal, if they're not equal, then they're not independent. And then conditional probability, the probability of A given B, then B becomes the, if you want to call it, the limiting factor. It's the new denominator. And the two events occurring, A intersection B, is the numerator. And all these formula, it's really important that you appreciate that probabilities are proportions, which means I can change that P to n's, in other words, counting the number of elements, and the formula apply as well. It applies thinking about P, the probabilities. It also applies when we're counting number of elements. So keep that in mind depending on the structure of your question. And obviously what you would expect in work is to have to rearrange formula to find the particular region that you're interested into. That's the word I'm looking for. Not variable, region that you're interested in. Now we have that. Let's do a question. Let's do one more to wrap up in terms of this theory and me lecturing per se. And then I feel reasonably satisfied I can let you loose to do a problem set on this, to really work more independently and see where you go with this. So let's do one more, explore one more idea together. And here it is. Here's a question for you to do that I will go through in detail after. So use the power of the pause. You're working through this one. Back in the day, this was a 7 marker. Well, I've modified it. It was actually an 8 marker, but yeah, we'll work with it on this for all purposes. Off you go. Try and do this question. Brilliant. Time for me. So the first bit, we had to determine if the events were, and I'll go to another slide with the Venn diagram there. Okay, did I have that? Yeah, got that right. And what I'll do, I'll work out the probability. So for A, we want to check if events are independent. So what are we doing? We're going to see if probability of A, we're going to work out probability of A multiplied by the probability of B, and we're going to see if it's equal to the probability of A intersection B. We have A intersection B. The value of A intersection B is, and I won't use the equal sign because we don't know as yet, is 0.08. And when we do probability of A multiplied by probability of B, what do we have? We have 0.22 multiplied by 0.21, and that's going to give me 0.4. Let me just so I'll just put in my calculator here, 0.22 star 0.21, and that is equal to B 0.04. That's the answer we're looking for there. So 0.0462. That's what we have, 0.0462, which is not equal to 0.08. That means that the events are not independent. Okay, events are not independent. Dr. Handwriting, not independent. So that's 2 marks there. We plug in, we work out probability A times probability B and compare it to probability A intersection B. For part B, we want to draw the Venn diagram. Drawing the Venn diagram, we have the overlap, the intersection, so I can put that in as 0.08. That's probability A intersection B. And then to get the probability of A, I need to take away that 0.08 from 0.22. So 0.08 needs to be taken away from 0.22. And you should get 0.14. 0.14. 14 and 8 gives me 22. And similarly for B, we're not getting 0.22. We want to get 0.21. So we'll have 0.13. I now have all the regions that make up A union B, and what I need to work out is what is A union B prime, the missing element out there. And to do that, we will do 1 take away 0.14 plus 0.08 plus 0.13, and just reminding you that is 1 take away the probability of A union B, the complement of A union B prime, and when we work that out, we're going to get 0.65. 0.65 is what we're getting. 0.22 plus 22 and 30 and 35, so 65. 0.65 is what we have there. That's part B. And finally, part C, the newest kid on the block, the given. We have that formula for conditional probability. I'll scroll down to deal with that. So just going down, giving myself some space there. And the probability of A given B, well, to find that, B is the limiting factor, so I need to have the probability of B as my denominator in this case. And I'll write down the formula, probability of A intersection B divided by the probability of B. The probability of B, 0.21. The probability of A intersection B, well, we're reading it off from the Venn diagram, it's 0.08. So 0.08 divided by 0.21. That's what we want, 0.08 divided by 0.21, and that will give us 0. On the calculator, you should get 0.381 as your solution. 0.381 is the probability of A given B. I'm going to stop there. I think we're ready to go. The only thing we haven't touched on, but I'll leave it as far as I can recall, and I'll leave it for the problem sets. And don't worry, as we go through problems, you have a problem set to work out. Interesting things will pop up, but I think you're well equipped from the 3 sessions we've gone through on this topic and set notation, Venn diagrams, and probability. And I hope you feel well equipped as well. That we have left out is interpretation. So when you get these answers in a story, in a context, to write a comment of what it means going from set notation back to plain English. But you'll experience that in the problem set. All the best to you, and I look forward to going through some interesting problems with you. That's all for now.